Hi everyone, my name is Chong and welcome to my presentation about making nerves relightable. This was joint work with Guojun, Chen, Dong, Pieter, Hongzhi, and Tong. Let's start with our goal, namely free viewpoint relighting, with full global light transport of objects possible with ill-defined geometry and complex material properties, using only hand-captured unstructured photographs. We achieve this goal by optimizing a directly relightable nerve for each scene such that the error with respect to the captured images is minimized. Our method can achieve similar quality results from around 500 input images compared to previous state-of-the-art relighting methods. An advantage of using a directly relightable neural representation is that there are no limitations on object shape or the material properties, as well as that it can embed all the global light transport effects in the captured scenes. Before detailing our relightable neural representation, let's review how a regular non-reliable nerve works. Nerve evaluates the color at a pixel by sampling points along camera rays. At each sample point along the camera ray, nerve queries the neural radiance field given the sample's position and ray direction. The result from the query is the corresponding color and the density at that point. All colors and densities are gathered in the end through the volume rendering equation to get the final color. To enable relighting, we change the original radiance field by adding the light position as an additional input parameter for evaluating the MLP at each sample point. We supervise the training of this relightable nerve with ground truth images rendered from random wheel and random light positions. While this simple extension enables relighting, we observe that it struggles to model high-frequency light transport effects, such as sharp shadows as shown in the rendered image of a basket scene. The naive relightable nerve also fails to properly reconstruct specular highlights, such as the one on the inside of this cup. The key problem is that the inherent spectral bias of the underlying MLPs prefers low-frequency signals, making direct modeling of these high-frequency light transport effects challenging. To overcome this challenge, we supplement the input to the MLPs in the neural radiance network with additional shadow and highlight hints. Critically, we do not impose how these hints are combined with the estimated radiance, but leave it to the network to decide on how to use these hints. Now let's look more in detail in how we compute the shadow hints. To help the network model sharp shadow edges, we estimate the light source occlusion of each point in the volume by tracing a secondary ray through the neural radiance field. While this process is relatively cheap for a single shadow ray, performing a secondary ray march for each primary ray's sample position is computationally expensive. To speed up computations, we approximate light source visibility of a whole primary ray by shooting a single shadow ray at the estimated depths. However, we found that the result is still very blurry because nerve introducing bias in the depths and the estimated depths tends to be smaller than the actual depths. This depth bias in nerve was also observed by Wang et al., who introduced news as a solution. By using news instead of nerve, we obtain an unbiased depth and thus more accurate shadow hints, resulting in more accurate high-frequency shadows. To compute highlight hints, we first extract the surface normals as the normalized gradient of the nerve's sign distance field. Next, we compute highlight hints by evaluating a GGX microfacet BRDF model using the extracted normals. While straightforward in theory, in practice we do not know what roughness to use for evaluating the GGX BRDF model. To avoid selecting or estimating a single roughness value, we instead offer the network multiple highlight hints computed using 4 different roughness values. As like the shadow hints, we let the network decide how to use the information from these 4 highlight hints. Using these multi-roughness highlight hints, our network can now accurately reconstruct high-frequency highlights on the object. Now let's look at some examples. In these 3 examples, you can see sharp shadows cast on the ground plane. Also note the accurate reconstruction of sharp highlights on the ball. Our method is not limited to a specific material. We can handle objects with highly specular appearance, anisotropic material, and subsurface scattering. And even furry objects with ill-defined shapes are not a problem for our implicit shape representation. Our method, of course, also works well on typical nerve test scenes such as the drum set, the hot dog, and the Lego scene, except that, unlike classical nerve, we can change the lighting now. To apply our method to real-world objects, we follow the capture process of deferred neural lighting and light an object using 2 cell phone cameras, one for changing the wheel and one for independently changing the lighting. However, the resulting relightable neural radiance field exhibits some blurring. This is caused by small errors in the camera pose estimation. We resolved this blurring by jointly refining the camera pose estimates during training. This camera pose refinement strategy greatly reduces the blurriness of the relightable neural representation. Here are 3 examples of newly captured scenes featuring a variety of materials and shape complexity. We also compare our method to state-of-the-art relighting methods. We first compare to iron, which uses co-located lighting for capturing and assumes a GGX BRDF model. This model ignores interreflections, leading to distorted geometry and inaccurate relighting results. We also compare to a state-of-the-art neural radiance transport method called NRTF. Without hints, NRTF struggles to accurately reproduce high-frequency light transport effects, such as hard shadows and specular reflections. Recently, Philip et al. Introduced a pre-trained neural relighting network. This differs somewhat from our method, as we train a network per scene instead of pre-training for all possible scenes. Nevertheless, it is still a valuable comparison. We can see that Philip's method struggles to reproduce the correct appearance even when providing ground truth geometry. Finally, we compare our method to deferred neural lighting. As you can see, we observe a very similar quality, but with only a fraction of the input. To summarize, we introduced a relightable neural radiance field which supports 360-degree free viewpoint relighting with full global light transport, and only using unstructured captured input. Key to our method is the inclusion of shadow and highlight hints to help model high-frequency light transport effects. Possible future directions include supporting efficient rendering with environment lighting and reducing the acquisition cost further by leveraging active lighting. Thank you for your attention. Please visit our project page for more results and details. Our code and data is also available.